So welcome back to the sixth and last session of LOPSTR. And in this very final session, we will have actually a speaker that is going to present the best paper, or the paper that got the best paper award. So that's Fabio Fioravanti, sorry, going to talk about constrained horn clauses satisfiability via catamorphic abstractions. Thank you.
Okay. Thank you. So this is joint work with Emanuele de Angelis, Alberto Pettorossi, and Maurizio Proietti. And I will start by giving a brief overview of the use about the use of constrained horn clauses in program verification. Then we will focus on the use of constrained horn clauses that use algebraic data types, such as lists and trees. And here we are interested in properties that are specified by using catamorphisms that you can think about as total functions or functional predicates in this case, with a fixed recursion schemata. And then I will show you our transformation that is based on transformation rules and is guaranteed to terminate and preserve the satisfiability of the clauses, and is based on the adaptation of the usual rules for defining, unfolding, and some other rules that are specifically conceived for dealing with catamorphisms and algebraic data types. And then I will show you the experimental evaluation, the results of the experimental evaluation. So constraint clauses are actually the same as constraint logic programs and Prolog. They share the same syntax and semantics, but usually they're not intended for direct execution, but are instead used as an intermediate language for expressing the semantics of programming languages and properties. So usually one translates the program and the property to constraint clauses and then checks their satisfiability. If the property is valid, if and only if the clauses are satisfiable. This is the standard approach. And horn clauses can be used for verifying properties of different kinds: partial correctness, relational properties, termination, resource consumption, and so on. And we can derive clauses starting from programs that use different paradigms: imperative, object-oriented, functional, smart contracts. There is a workshop. Maybe many of you know that there's a workshop that is organized every year since 2014, and it's called SCVS, or Close Verification Synthesis. That is a very interesting workshop, so take note of it in case you want to submit a paper, because I'm the promoter, one of the promoters of the workshop. I would like to attract you, to invite you to contribute. And there's a CSC competition of solvers, and there are very good solvers for checking satisfiability of CSCs, such as Z3, Eldarica, Golem, and many others. CSCs are used by several communities other than LOPSTR, but also ICLP, CAV, previously in PLDI, in Popl, TACAT, and so on. And they're also used in industry. Microsoft, Amazon use CSCs, and Ethereum uses CSCs. In particular, for those of you who know Ethereum, the blockchain platform for smart contracts written in the Solidity language, and the Solidity compiler as a model checker that translates the solidity code to on clauses and then checks the satisfiability and the correctness of the code using backend CHC solvers, just to have an overview about the use of clauses or program verification. Then, however, state-of-the-art solvers have difficulties improving satisfiability of clauses that contain algebraic data types such as lists and trees. And so instead of extending the CHC satisfiability checking in order to deal with these lists and trees, these ADTs, we follow a transformational approach by which we transform the clauses into an equisatisfiable set of clauses. And the transformation, as I told you, preserves satisfiability. So the initial set of clauses is satisfiable if and only if the final set is. And the transformation always terminates when properties are specified via catamorphism. The experimental results show that the transformation improves the effectiveness of the CHC solvers that were not designed for dealing for ADTs. And in this paper, we improve over the work we did we presented in previous papers, as we do not need auxiliary lemmas for specifying properties of auxiliary functions used by the programs that we are going to verify. No information for multiple queries, but instead for each ADT sort, say in the example list of integers, we define the set of relevant catamorphisms. We call it the catamorphic abstraction. And then we also augment the clauses with ADTs using clauses without ADTs. And this is a crucial step that enables standard CHC solvers to be more effective in discovering the relation among variables that are useful for proving the satisfiability of the clauses. The satisfiability or the unsatisfiability, of course. What are catamorphisms? So intuitively, they are predicates that are total and functional with respect to some of their arguments, and are defined by simple recursion schemata. Examples as list length or tree size. Let's see in this slide a template for the list catamorphisms. We have two clauses here. One clause deals with the empty list, and the other clause deals with the non-empty list with just one argument exposed. And it calls the predicate name is h, and h also there's a call to h in the body on the tail of the list. This recursive call produces a result, and the result, the final result, is obtained by combining the result R with possibly with h. Okay, by combine 1, h, r, res. Where combine 1 and combine 2 below are total functional predicates or constraints, not necessarily catamorphisms themselves. So, for instance, the predicate computing the length of a list matches the schema, as you see, length of the empty list is 0. The length of non-empty list is computed as by adding 1 to the length of the tail of the list. Okay, and the binary tree catamorphism schema instead is very similar, but instead it has a clause for the base case of the tree. There's a leaf node, a leaf. And then the recursive case exposes the node, the element, and the left and the right subtrees, and there's two recursive calls to the left and right subtrees. So the predicate computing the size of a binary tree you can see that is an instance of this schema. Actually, we extend this, the standard notion of catamorphism by allowing extra parameters that allows us to define predicates that says, for instance, for specifying that X is less or equal than all elements of a list L. For a list, or for counting the number of occurrences of an element in a tree or in a list. By further extension, we add extra function calls. In this way, we are also able to expect the properties such as the one saying that a list is sorted. And for trees, by adding extra function calls, we can specify even the binary search properties of a tree. So we can see that a tree is a binary search tree. So let's start with an example. Let us consider the program specifying the predicate double, where double xz holds if and only if z is the result of appending x to itself. So the definition of double is on this row. We create a copy of x, and we append x to this copy, thereby producing z. Then there's the usual definition for append. And we have a catamorphism here, count, that counts the number of occurrences of an element in a list. And the result is in the last argument. In the query, the property we want to verify is that there is no element that occurs in Z and not the number of times, because we are duplicating a list, so then no element can occur not the number of times. We can write it this way in the query form. So we put here the negation of the properties that M is odd, and this should be false. Okay? How do we proceed now? We, for every ADT sort, tau, we define a catamorphic abstraction that is a conjunction of catamorphism that we are interested in. So if tau is an ADT sort, we introduce a conjunction of katas, like you see here, where T is an ADT variable, and X and Y are tuples of distinct basic variables, not ADTs, just basic variable. By basic variable, we mean integer, booleans, and so on. Okay? And that are pairwise disjoint. And these katas are distinct catamorphs. So, for instance, for the list of integers, going back to the example, for the list of integers, we can introduce the catamorphic abstraction that says that we are interested in counting the number of occurrences of elements in a list. And so the kata is just this one, count x ln. Then, given the catamorphic abstractions for all the ADT sorts used by the program, then for each program predicate, we get a catamorphic abstraction specification of this form, where P is a program predicate, and this this is a conjunction of atoms where these are catamorphins, and X is a tuple of distinct basic variables. TIs, these variables underlined here, T1, Tk, are all the T variables occurring in Z, in the code, and they're possibly not distinct. And X and VIs are tuples, again, of distinct basic variables that do not occur in Z. So, for instance, going back to our example, for double, since X and Z are list of integers, and our catamorphic abstraction for list of integers tells us that we are interested in counting the occurrences of elements in a list, we get this conjunction. We count the occurrences of X in the first argument, and N1 is the number of such occurrences, and N2 is the number of occurrences of X, or element X, in the second ADT argument Z. This is the result of appending the two lists. And so on for the other program predicates. Then we proceed by transformation. We start with the clauses that encode the program of interest, the query, and the catamorphic abstraction. And we start by defining new predicates that contain just one program predicate and some catamorphins for properties. Then we unfold the program predicates once, and then we unfold the catamorphins with non-variable ADT arguments as long as possible, as long due to the structure of the catamorphism, this is guaranteed to terminate. Then we possibly add catamorphism atoms to the body of unfolded clauses, and then we fold using the definition we introduced during the first step, and we replace in the body of clauses goals with heads of clauses added by definition. At the end, we derive a new set of clauses by erasing ADT arguments, and we add the atoms with the erased atoms to the folded clauses. Let's see each step briefly. Then definition are introduced for definition for new predicates. Predicates not occurring in the original program are automatically introduced using the query and the catamorphic abstractions for the program predicates. So we introduce in our example these three definitions. Then we unfold the program predicate in a definition once. So if we have this definition clause here, we unfold double, and we replace double with the conjunction equal append. Then we repeatedly unfold catamorphins with non-variable ADT arguments. In this case, there are no such catamorphins. And then we repeatedly apply catamorphins functionality. Again, there is no such, this is not applicable in this case, but this allows us, for instance, to replace this conjunction of two catamorphins, count AB C1, count AB C2, by this conjunction where we drop one of the catamorphism atoms and replace it by an equality, because we recall that these are functional. So C1 should be equal to C2. It's not. We don't need both. Then, using the catamorphic abstraction specification, we possibly add catamorphism atoms to the bodies of the unfolded clauses. So for instance, this is an unfolded clause, and the catamorphic abstraction specification includes this expression that says that for EQ, I'm interested in counting the occurrences of X in the first list and in the second list. And going back here, I see there's just a count on the first list. There is no count on G. This is the second argument. And so I add the count for it. Note that I is a fresh variable, so I'm preserving the satisfiability. I is existential, can be anything. Then, using the definitions, I fold, that is, I replace an instance of the body of the definition by the corresponding head. If we go back to this slide, we see that we had a clause with EQ and append. These are the definitions that have append and EQ in the body, and we replace EQ and append and the catamorphins that are bound to the variables occurring in these atoms by the corresponding head, nu2 and nu3. Note that folding derives clauses when there are no catamorphins, there are no program predicates, they're just new predicates, the predicates we introduced by definition. Now we derive new clauses by erasing ADT arguments from the clauses that we have obtained by folding. So you can see the folded clause here with the ADT arguments underlined, and we derive a new version of this clause where for each predicate symbol we introduce a new predicate symbol without the ADTs. So new one, because new one without ADTs, we just project away these arguments. We drop them. And actually this is, and we produce an abstraction of the previous set of clauses. Existing solvers are good on clauses without DTs, but since this is an abstraction, this is good for proving satisfiability, but not for proving unsatisfiability, because if you prove unsatisfiability in the abstraction, it could be a spurious counterexample. And but we do not use this abstraction directly. Instead, we add this abstraction to the equisatisfiable clauses. By doing so, solvers are much more effective in discovering the relation between the constraint relating these basic variables. And so we derive this final set of clauses starting from the original clauses for double, the query, and the catamorphic abstraction. Now I'm ready to show you the results of the experimental evaluation that has been performed by using VeriCat apps. They use this very catamorphic abstraction that is implemented on top of VeriMap. This is our original system for CSC transformation verification. So we, starting from our discloses, the query, and the catamorphic abstraction, we apply this transformation algorithm and produce clauses that contain ADTs, clauses without ADTs. Then we translate this clause to the SMTLib format, and then we invoke the state-of-the-art solvers, such as G-Twin and Eldarica, and then the output is either SAT or unsat or timeout. That's unknown. And the benchmark consists of 150 programs for concatenating, permuting, reversing, and sorting over list of integers. For sorting, we use different algorithms: bubble sort, heap sort, insertion, submerge, quick sort, selection, and tree sort. For element insertion, deletion in binary search trees. The properties that can be defined by using catamorphies include the length of the list, tree size, tree height, minimum and maximum element of a list or a tree, sortedness of a list, binary search tree property, heap property, balanced tree, sum of elements of a list of a tree, or content of a list as a set or multi-set of elements. In this table, I will show you the result of our experimental evaluation. In the first column, we have the program, list deletion, permutation, reversal, sorting algorithms, binary search tree. And we have properties, SAT and unsat properties. So properties should be either valid or not valid, so the output is SAT or unsat, respectively. And in these columns, we have the results of running Eldarica before source and after the transformation. So we run Eldarica on the source clauses before the transformation, and we also run Eldarica on the source clauses after transformation. And the same we do for Z3, before and after. And the last column shows the transformation time in seconds. The first observation is that state-of-the-art solvers are very good at proving unsatisfiability, not satisfiability. That is a finding bugs, not proving that there is no bug. So, for instance, Eldarica on the source clauses clauses is able to prove 5 SAT properties and 69 unsat. But after the transformation, it's able to prove 39 SAT and 59 unsat. So there's an increase in the number of SAT and a decrease in the number of unsat. This is probably due to the fact that Eldarica is often very close to the timeout, even for the properties that are proved unsat. So maybe giving some more time to be able to prove them. Whereas if we look at the result for Z3, Z3 is extremely effective at proving unsatisfiability. It's able indeed to prove the unsatisfiability of all 75 properties, but of no satisfiability property. So 0, 75 before, and after transformation, the result is that it's able to prove the satisfiability of 70 and still be able to prove the unsatisfiability of all the 75 properties. So overall we get a plus 70 satisfiable properties with the solving time below 1 second. The other observation is that the transformation introduces a small overhead because the transformation time is almost always below 1 second, very fast. So this is a complete and sound transformation that works well for verifying property of clauses with ADTs written using catamorphisms. The advantage of using the transformation approach is that we are able to separate the inductive reasoning done by the transformation from the solving part done by the CHC solvers. And this is also largely independent from the constraint theory. It can be, so we usually linear integer arithmetic and booleans, but we can use any constraint theory supported by the SMT solvers. What about the ongoing future work? We are working on the automatic discovery of useful catamorphisms for further reducing the burden of the programmer and specifying the properties of interest and extend the applicability condition of the method. We are using catamorphisms because they have good property, they ensure us the termination, and they're functional, but we would like to relax also that and a bit still guaranteeing the termination of the process. We would like also to compare with other solvers that were specifically designed for working on ADTs, the most notable of which is Racer Z3, Popol 2022, but it's very good. It's very good on the unsat instances again, but even in that version, it was less precise than the tool we used 2 years ago. So we are confident that we are better. This is an issue that there are different input formats, so they're not just SMT-lib clauses. You have to annotate predicates and write extra stuff. So it's not very easy to do an extensive comparison. Maybe we'll do it in the next edition of the CHC comp. And a medium-term objective is using our transformation approach as a backend for program verifier, like Daphne, Stainless, and Y3, for instance. Oh, that's all. Thank you.
Thank you very much for that. Any questions?
So thank you very much for the great talk. I was wondering about extensions of those catamorphisms with some kind of perhaps. First, can you have ADTs as results of those catamorphisms, or is it really important that, let's say, the result of the catamorphism is a base type, a base sort, for the Horn constraints?
Actually, as the result, you mean as the output?
Yes, because if you can extend the results to other ADTs, you may be able to encode some effectful iteration on ADTs. So, for example, if the output of some list iteration is a sum type, you can represent an exception that could occur during traversal of the list. And that might be applicable in quite a few settings, I believe. Maybe.
Actually, currently we do not allow ADTs as outputs, but of course they can be extended. For instance, you could extend. You have to be very careful, however, on the structure. So if you have to be sure that by doing so, you don't lose the termination by allowing some ADT arguments to go, and so you're not able to unfold unrestrictedly, but you have to stop somehow, and maybe generalize, introduce some generalization mechanism in order to deal with them.
Okay, thank you.
Thank you.
Yeah, thanks. Very interesting. And I was just wondering whether you saw any connection to the kind of things that Manuel was talking about this morning. I mean, is there some way that you can use catamorphisms to design an abstract domain which will then help you to verify some assertion? I mean, he used similar examples, sortedness and so on.
Yeah, indeed, one of the ideas was to use the Chow analyzer in order to verify whether predicate is actually a catamorphism, so to verify whether it's...
To verify whether a predicate is a catamorphism?
Is a catamorphism, yeah. Because in principle, you don't know whether it is. Now we assume that that some predicates are catamorphisms, because they are total and functional. But in principle, you should be able to discover it from your input by guessing which could be the output argument, and check whether it's functional and whether it's total and so on. So one possible direction is that of using the Chow analyzer for discovering this information. But of course, we are assuming that these predicates are catamorphism, but we could also verify by using our other techniques. But that's
Maybe just a final question from me. You focus only on transformations that are equi-satisfiable. Where does this restriction come in, and why?
Because
Maybe I
we
missed
also would like to check whether a property is invalid, does not hold.
Okay.
So if you, in previous work, we produce an abstraction. So if you got an answer unsat on an abstraction, you're not sure whether it comes from the real traces, so to say, the real paths inside, or in the space you introduce by abstracting.
Okay.
And so that's why we are interested in preserving satisfiability.
Okay, so thank you very much. If there was no further questions, thank you very much.